In this video, we are going to discuss calculating limits by using a number of different limit laws. First off, for the notes on this, it's going to be expected that you'll spend a lot of time pausing the video so that you can copy down the notes from these pieces. There is a lot to learn in this section. Our learning objectives are fairly straightforward. First, know what the 11 limit laws are, 2 limit properties, and 3 limit theorems. So 15 things that you have to know, and then recognize those strategies, recognize those laws, properties, theorems as strategies for problems, and then apply them to get answers. So fairly straightforward. You have to know the 15 things, you have to be able to pick when they're the best strategy, and then actually use them to get answers. So, here are the first 5 limit laws taken directly from the textbook. In these pieces, the letter C represents a constant, and we are making the assumption that the two limits, the limit of f of x and the limit of g of x at the same number a, exist. So we are doing pieces like the limit of x squared plus x as x approaches 2. Basically, this says if you have an addition of a function, you can actually split it up into 2 limits, as long as both limits exist. If it's addition, you can split them up as 2 different pieces. Same thing for subtraction. If you had x squared subtract x, you can subtract the 2 limits. If you have a piece that is doing a product, and I'll erase this stuff and come back. So if we had limit of, as x approaches 2, of x squared times x, or times 2x, we would be allowed to split it up into 2 separate limits. A limit of the first part multiplied by the limit of the second part. That's limit law 4. If this were division, where we had, generally it would be written x squared over 2x instead of using the divide symbol. Yes, Scotty asked C is a constant. That is correct. So the short version is, if you have functions where you're adding, subtracting, multiplying, dividing, you can just split them up into add, subtract, multiply, divide of the limits. Same piece where this limit law 3 is saying, like if you had the limit of x approaches 4 of 3x, you could actually take the constant 3, pull it outside the limit, and say, do it that way. The question was asked, why would we want to write it like this? Generally speaking, you don't write it. This is just being done to say, hey, these are the strategies you'll be able to use. You're allowed to do them. Most of the time, you're going to wind up doing this thing in your head. But if you're using it to, like, say, prove a theorem, you may want to write it up this way just so that you can say, instead of x, like f of x. That way we could work with just f of x instead of 3 times f of x. Verbally, this is saying for the first part, if you are going to take one limit of two functions being added together, another way you can do it is to split it up as two limits and add up the two limits with smaller, simpler, easier functions. And you notice how I had yellow written there for sum? Change it to difference. And it's the exact same thing for number 2. Exact same words, just difference instead of sum. Change it to product, and you get number 4. Exact same thing. Change it to purple here. Change it to quotient. It's the exact same thing. All works out. Exact same words. Number 3 is a little bit different. And I'll go with green on this one. Basically, it's almost like the distributive property. You can factor out constants and leave behind the limit. That's what this piece is saying. Incredibly, incredibly important rules. These will be your 5 most important tools when you're working with limits, because otherwise you wind up with things that are just god-awful huge and complex. This is a way of taking the really complex functions and splitting them up into smaller, simpler, easier functions. So, continuing then with our pieces. Here's where we're going to start off. Use the limit laws and the graphs of f and g to evaluate these following limits, if possible. Please remember, these laws are starting with the assumption both the limits exist for f and g. If the limits don't exist, obviously you can't add things that don't exist. So, what is this first one saying? You notice how it's saying 5 times f of x? We could take out the 5 and just say, what is the limit of f of x as x approaches negative 2? You also notice how we have subtract g of x? So we can subtract the limit as x approaches negative 2, the exact same a value, they're approaching the same number, and these are pieces that we can get with the calculator, or the graph. As x approaches negative 2, what is happening to f? Okay, here's our graph of f. There's negative 2. So, coming from the right, coming from the left, Scotty was correct. That's closing in on a 1. Looking at the graph of g, there's, hang on a second, I have to back this part up because I was looking at something incorrectly. 0, okay. I just wanted to verify my axes. This was 0 there. The reason I paused, I was starting to think the 0 was being applied to here, in which case each tick mark would have been counting half, which would have changed the way we had to look at things. Upon looking at it more closely, I do see that the 0 is being applied to this for the x-axis and that we were correct. It just, for a moment, my brain got a little bit fuzzy and I wanted to make sure that we were doing it correctly, so that's why I paused. Sorry if that pause confused you. Finishing this particular problem, though, we still need the limit as x approaches negative 2 for function g. That's a negative 1. So we will subtract negative 1. Just crunch the numbers. 5 subtract the negative 1 The first answer is 6. I'm going to need to erase the blue to create room for the next one. Of course, you can pause the video, you can backtrack through the video. This piece is the same. The limit of the product f of x and g of x as x approaches 2, we can multiply the two individual pieces. So as x is approaching 2, where is f going? About 1.5. Where is g going? Over to 0. So when you multiply them, we have our answer for f, or for this limit. Fortunately, we have the same pieces here. G of x over f of x as x approaches 1. Now, as I said, this is a piece that most of these rules are going to be things that you'll... These are things that you will do, for the most part, in your head. It's not typical to actually write out this first line like we had done here in the red. More generally, you'll just look at it and say, what is the limit of g of x as it approaches 1? Well, there is 1. What's the issue there? G approaching from the left is a negative 2. G approaching from the right is negative 1. The left and right hand limits don't match up, so the g of x limit does not exist. If we put that over f of x, does it even matter what the f of x is? Part of it doesn't exist, so the whole limit doesn't exist. It just, who cares? It does not exist. It is actually possible. If we also had the same type of jumping problem with an f, it is possible that the jumps could wind up canceling themselves out. Yeah, so it might work in general, but this is, if it exists, these are shortcuts. Remember, the rules are shortcuts to be able to do it based on the assumption that both of the limits exist. If the limits do not exist, these shortcuts don't work, but that doesn't mean that you can't do it anyway with other techniques that we have not yet developed. So, continuing. Here is a theorem. The limit of f of x to a power of n is equal to the limit to a power of n. Why would this be true? Consider this. What if we took the limit as x approached some number a of f of x times g of x? What did our previous theorem say we would be allowed to do? The previous theorem said we could split it up as two limits. Okay? What if we replace the function g with the function f? So in that instance, g of x equals f of x. We could still use the same function, the same theorem. The only difference is this g is replaced with an f. That is used to show us that the limit, as x approaches a, of f of x, where the f is being squared, is instead now the limit being squared. You see it? Now what if we then took those same pieces and said, multiply by another f of x? Then it becomes a cube. which would give us another times a limit, which becomes a cube. And if we did it to a fourth power, a fifth power, a fifth power. We could do a proof of this fairly straightforward using the principle of mathematical induction. I'm assuming that that was a proof technique that you discussed in your previous classes, yes? If not, we'll have to find some time to discuss PMI and rehash how that was done. Okay, what about these ones? Here are some more properties for us. The limit of a constant equals the constant. This would be something like saying the limit of 5 as x approached 2, that will be 5. Can you explain why that would be true? Consider the graph f of x equals 5. What does that graph look like? Yeah, it's a horizontal line. Basically, we're doing y equals 5, f of x equals 5. Well, as you go x equals 1, x equals 2, where is it going? Right at 5. Very quick visual proof of what's going on with it. Jumping to the other side, we have the limit of x as x approaches a. Yes, these are some of the laws. Specifically, we mentioned back at the beginning that there were 11 limit laws. Here were the first 5, numbered 1 through 5. Then we had limit law number 6. These are limit laws 7 and 8. Okay, so this would be a piece that's like limit as x of x as x approached 2. It's going to be a 2. Why? Well, we could do a quick graphical proof again. There's the graph of y equals x, or f of x equals x. And if we go over to an x value of 2, where is it going? To the y value of 2. From both on left and right hand sides, they're going to match up. Very quick visual piece, fairly straightforward to see. Limit of 9, or limit of 9. Limit law number 9. This one is saying if we took something like the limit of x to the fourth power as x approached, say, 2, that answer will be 2 to the fourth. Now, why would that work? Take a look at the hint. If we go back to Law 6, Law 6 told us if we take the limit of f of x to the nth power, if it was done this way, if we use the identity function f of x equals x, that can be replaced with an x, and so then the other f of x could be replaced with x. And if we were going x approaches 2, basically what this piece is telling us is if we had a graph, and I'm going to pick x squared just as an exemplar, if we had the graph of x squared as x approaches 2, you come up, you come over, 2 squared would be 4. This is the case for n equals 2. If we did the case of n equals 3, Well, you come over to an x value of 2. You come up to its height. 2 cubed would be 8. This one was 2 squared was 4. You see the structure behind it? That because this is a basic power function, we know the left and right hand limits are going to come out nice with each other. There's not going to be a hole or something with a power function. It's giving us a very quick way that if we have a power function, we can basically just substitute in and get our values. Same piece works for roots for the same reasons. If we were using, instead of f of x equals f, and instead of using f of x equals x, we could have been using f of x equals 1/2 or 1/3. F of x equals 1/4. We could be using the second, third, fourth powers and still done the same technique to show this part. Short version behind this is if we had the limit of, say, a square root of x as x approached 5, it's just going to be the square root of 5. One huge piece worth noting, though, n is a positive integer. So this is not a 1 over case. We're talking about actual roots, like the second root, third root, fourth root, fifth root. And additionally, if we have an even powered root, we assume we're working only with positive numbers. Big reasons why, of course, is if we are doing a square root looks similar to that. Can you plug in the negatives? Nope. That would give us the complex number I. We're not working with complex number I. So if you have an even powered root, so a second root, a fourth root, a sixth root, in order to avoid taking square roots of negatives, we're assuming that all of this is being done with positive roots. Of course, that's not a problem if you had a cubed root, because a cubed root actually works when you take a cubed root of -3, you can come down and get a y value that actually does exist. So the rule works when the function is defined. Limit law 11. Pretty much the same type of thing. This is for the graph of x. The same rule works for f of x. So this is telling us if we had a piece like limit x approached of, say, -4, or we'll just say +4. If we had the limit as x approached 4 of the fourth root of something like x squared plus 1. So we had a whole function. We can take the square root or the fourth root and actually pull it out so that we can just do this piece. Yes, this is similar in structure to number 6. Number 6 was basically saying if this was a counting number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and kept counting, well, it also works for 1 over 2, 1 over 3, 1 over 4 for the roots as well. So, whole lot of laws that we just went through. 11 laws. It's a lot. How could we use them, though? This first problem, I'm going to write out with the whole massive amount of stuff that's limit equals, limit equals, limit equals, and write it out the long way. In general, though, you're going to be doing more of these pieces in your head and not writing all this stuff down every single time because it's so much writing. But officially, what this piece is telling us that we have is we could factor out the 2. So we would have 2 times the limit x approaches 3 of x cubed plus 3 times the limit x approaches 3 of just plain x. Then we'd have to subtract 4 times the limit of, as x approaches 3, of the constant 1. Evaluating individual limits. 3 cubed. This piece right here, you notice how it's a power function? That power function is taking advantage of law 9. We can replace the x with the constant that it's approaching and simply say that's 3 cubed. Then we'd have 3 times, well, 3 can replace the x, minus 4 times, there is no x to replace, so it's just a 1, and we can crunch our numbers. This second step is typically where you would actually begin your writing. We know, based on the theorems, that we're allowed to do those things, but it's so much writing that most people don't take the time to write that step out. They'll go directly to evaluation of the limits. Instead, just start plugging it in and see what you get. In that instance, we would have 2 times 27, which is 54, plus 9, subtract 4. We get the overall answer, 59. We're noting this is telling us if we were to create a graph of that entire function in yellow, as we started approaching the x value of 3 from the left and the right, the y value height of this function would be at 59. As x approaches 3, the f of x value is approaching a 59. There's our interpretation for it. Example 3 is similar. How is this different? Well, of course, we can see that this top part here, we'd have 3 times the limit of x squared plus 1 times the limit of x plus the limit of 1 all over. Basically, we're seeing all these pieces that are coming in. Our first technique that we can try to use, it's not a guarantee that it'll work, but basically we know because this is going to break into so many limits, let's just start evaluating those limits. We would have 3 times the limit of x squared as x approaches 2. 2 squared. Plus the limit of x as x approaches 2. Plus the limit of a constant is the constant. This is our f of x over g of x component. Then we'd have the limit of a constant 5. Subtract 3 times. You'll notice basically we're just doing a direct substitution, replacing x with the number. In many cases, that direct substitution will work. It's not a guarantee every single time, but in many cases it does. 3 times 2 squared. 3 times 4 is 12, plus 2, plus 1, over 5 minus 6. That's 15 over negative 1, which equals negative 15. So, as x approaches negative 2, this entire function is approaching negative 15 in height. That piece that we were doing is the direct substitution property. We recognize right away that we could go through and write out a crap ton of limit. It's so much writing limit. But you noted right away that we could do a direct substitution. And if it's a polynomial, or if it's a rational function, that is guaranteed to work for all polynomials and all rational functions. You start doing other algebraic functions, it might not work. And of course, we are going to examine algebraic functions where it does not work throughout the course, such as this. Let's try a direct substitution. 1 squared minus 1 over 1 minus 1, 0 over 0, which does not make sense. So what are we going to do? This is a particular one where your previous skills in algebra will be beneficial. If we factor x squared minus 1, do you notice that it's minus a 1 squared? Because 1 squared is 1. We could apply the difference of squares formula to recognize that our numerator may be rewritten thusly. So then what? We can cancel out the common factors, which indicates, although they're not 100% equivalent in the terms of the limits, these are going to wind up being the same. We could actually use that algebra to simplify this and say this whole piece, in the limiting process, not in terms of the actual function, but the limits actually will be equal. One plus 1 equals 2. Please note, this does not say it's common for students to think that if this piece is our f of x, I have seen many students write out f of 1 equals 2. That is not true. F of 1 is undefined. The function, when we tried plugging in 1, didn't make sense. That was our 0 over 0 case. This does not say f of 1 equals 2. It says the limit approaches 2. Those are two very big things, two very different things, but students will sometimes make this mistake. You should avoid it. So, that particular problem was actually taking advantage of this piece. If you have two functions that are the same everywhere, except at the point where you're taking the limit, then their limits are going to be the same. Specifically, when we go back to this last problem, this would be our f of x. This would be our g of x. Are they actually the exact same function? No. They are not exactly the same because in f of x, x equals 1, or rather we should say f of 1 is undefined, but g of 1 is equal to 2. This is why they are not the same function. But everywhere else they are the same. This is just saying if we have two problems like this, where they're the same everywhere except one point of problem, we can still say the limits are going to match up. We were using this property in the last problem, even though we didn't specifically come right out and say this is what we were doing. We can use that property again here. What do you notice about it? This function g of x is equal to x plus 1 everywhere except when x is equal to 2. In which case, this is telling us that we'd have a piece that's like, we have this function x plus 1, like this, but at an x value of 2, there's a hole right there, and instead, you're going to jump upward to 5. This is our graph of g of x. Well, what's happening to the limit? Coming from the left-hand side, where is the height going? coming from the right-hand side. Where is the height going? What we're noticing about those is that if we were to change this to a function f of x that's equal to just x plus 1, then f and g are the same function everywhere except at x equals 2. Everywhere else they are the same. You see the behavior there. What this theorem lets us do is say this limit of g of x as x approaches 2 is going to be the same as the limit of this f of x as x approaches 2. Because everywhere they are the same except this one tiny little spot. Please remember, limits are not saying it is the function value. Limits are saying, where is it going? In many cases, the place it's going will turn out to actually be the function value. But not always, and this graph of g is an example of that. This is approaching 2 plus 1 to get 3. That is not the function value in g. But we don't care about the function value in g, we care about the limit value. And the limit of g is the same as the limit of f, which is equal to 3. This property will let us do problems like this, and more importantly, it lets us do pieces like this last one where we cancel out pieces that don't match up. Example 6. What do we have? So if we tried doing a direct substitution would say 5 plus 0 quantity squared subtract 25 all over 0, which is 25 minus 25 over 0, 0 over 0, which tells us we have some more investigation to do. Direct substitution did not help us here. You remember doing your difference quotient problems? What did you always do with the difference quotient? Expand it out, cancel out pieces, see what's left. Let's do that same piece. What is 5 plus h squared? Five plus h would be 25 plus 2h plus h squared. Then we'll subtract off the 25 all over h, which we'll have limit h approaches 0. What winds up happening? 25 and 25 gives us 2h plus h squared. Anna noted that we had the h factor out, leaving behind 2 plus h over h. And then we wind up with this situation where the h's cancel. So that gives us the limit as h approaches 0 of 2 plus h. Now direct substitution actually will avail us. Plugging in h equals 0, we get our final answer. It's 2. In many instances, if you run into an indeterminate form like 0 over 0, a lot of times the 0 over 0s will come from having a term that will cancel out after some algebraic manipulation. Frequently, not always, but frequently. Example 7, if we try doing direct substitution, what do we get? 0 plus 4 square root minus 2 over 0. So 0 plus 4 is 4, square root of 4 is 2. We wind up with the same problem of 0 over 0, and we say, crap, what do we do? Okay, if you'd like to factor, what's going to factor? Okay, we could say try to take out the square root, but it's addition. This isn't 4 times, so we can't split it up as like the square root of 2t or something like that. For this particular problem, first piece that I would try, what if we conjugate? Please note, I'm not saying that this is a piece that's guaranteed to work. I just look at it and say, conjugation frequently changes the way algebraic forms turn out. A lot of times it causes pieces to cancel. Maybe it'll work here, maybe it won't, but we can do some experimentation and see what we wind up getting. So limit t approaches 0. What do we have in the numerator? Remember, we're taking advantage with conjugation. We're setting up the sum of squares formula. The same way that before we had it set up where we had x minus 1 and x plus 1 was x squared minus 1 squared. We're using the formula in reverse. Because we have a plus 2 and a minus 2, that's our difference of squares formula. We would wind up with the first piece squared. So a square root times a square root is just the piece inside. And then we would have the second piece squared. Negative 2 plus 2. Negative 2 times positive 2 is negative 4. Or subtract 4. And in the denominator, we'd have t squared times our conjugate. What's happening in the numerator? Plus 4 and minus 4, those cancel, which gives us limit t approaches 0 of t squared over t squared times t squared plus 4 plus 2, but I had my piece going too long, so I've got to shorten my radical. That's exactly what we're noting. Jessica noted, wouldn't the t squares cancel? She's absolutely correct. I wanted to write out that intermediary stage in case someone didn't see it. But when they cancel, we wind up with, the limit as t approaches 0, 1 over t squared plus 4 plus 2. Will direct substitution work in this equivalent or this alternate form? Okay, when we try that out, direct substitution gives us 1 over square root of 0 plus 4 plus 2, which is 1 over square root of 4, which is 2 plus 2. And we get our final answer of 1/4. If you remember, we're going back to Algebra 2. There was a reason that they had you practice a bunch of stuff with conjugation. Took a while, but those things that you practice with conjugation are helpful here. So this particular limit is equal to 1/4. Even if we were trying to do this on a calculator with a numerical expression, with looking into it, would still be perhaps a bit difficult to actually see what was going on. Example 8. Show that the limit of absolute value of x equals 0. With this particular one, well, do you remember what the absolute value function is? It's saying x if it's greater than or equal to 0, and negative x, or opposite of x, if you've got negatives. This is one that's very, very easy to see graphically. what does the graph of absolute value look like? Not a W. This is the graph of x. That's the graph of negative x. And they come together to form a sharp corner right at the origin. So when you come from the left, we could note the limit as x approaches 0 from the left of absolute value of x is the limit of x approaches 0 from the left of negative x. And if we factor out the constant negative 1, we'd get minus 1 times the limit x approaches 0 from the left of x, which is negative 1 times 0, which is 0. That's the left-hand limit. We know if the left-hand limit equals the right-hand limit, then the total limits are the same. So if we took this piece and said, approach it from the right, approaching from the right, we would have just x. Actually, I'd like to rewrite it because it's shorter. It makes sense to write it. So we'd have limit x approaches 0 from the right of absolute value of x. Based on our piecewise function, that's just plain x, which is equal to 0. Left-hand limit equals right-hand limit. Therefore, the total limit is 0. We can do that graphically, in which case it's very, very easy to see it's going to 0. Or we can actually do it analytically or algebraically with the actual equations. Example 9. Prove that this limit does not exist. Okay, if we tried direct substitution, 2 minus 2, 2 minus 2, we wind up with 0 over 0. No, because 2 subtract 2 is still 0. Well, we could do this problem the same way that we had done before. Similar in structure. If we were to take the left-hand limit as x approaches 2 from the left of absolute value x minus 2 over x minus 2, this is a piece that would note, since we're approaching from the left, these are negative numbers. Because we're taking like 1.9 subtract 2, that'll be a negative. So that would be telling us that we have the opposite of x minus 2 over x minus 2. When those simplify, cancels and cancels, you get negative 1. If we take the right-hand limit, the right-hand limit is telling us 2 subtract 2, like 2.1 minus 2 would be a positive number. Because it's a positive number, it's going to be the same thing that it is, just x minus 2. Well, when they cancel, we wind up taking the limit as x approaches 2 from the right of 1, the constant, which is 1. This is a different one. This one is showing, in example 8, we were showing that the limit is equal to 1. We're saying it does not exist. Well, to show that this does not exist, we need to show that the left-hand limit and the right-hand limit don't match up. Because they're not going to the same value, they don't work, we're done. Example number 10. If f of x is this piecewise defined function where we have the square root of x minus 3 And that's, I have a typo. This is supposed to be if it's less than. I apologize for my typo, I'll fix it here. This is supposed to be less than 3. Determine if the limit exists. Please remember, the limit exists if the left-hand limit equals the right-hand limit. So if we take x approaches 3 from the left, and it actually does equal the limit approaching from the right, if this is true, the limit exists. If it's not true, the limit does not exist. Okay, so if we are approaching f of x from the, if we're approaching 3 from the left is telling us we have values that where it's x is less than 3. With x is less than 3, that tells us we're using the bottom part, 6 minus 2x. And if we're approaching from the right-hand side are for values that are greater than 3, which tells us we are using this value. Well, let's evaluate these two one-sided limits then. As x approaches 3 from the left, we would have 6 subtract 2 times 3. That's closing in on 0. And if we're approaching 3 from the right, we'd have 3 minus 3 square root, which is the square root of 0, which is just 0. Now please note, this 3 is coming in from the right-hand side, which means we have a little bit bigger than 3. And if it's a little bit bigger than 3, then when we subtract it off, we get positive numbers. That is taking square roots of positive numbers, so it does actually exist. We're not having issues where we're taking square roots of negatives and having pieces outside the domain. It does work. Example 11 needs a little bit of a background. The greatest integer function, which is also sometimes called the ceiling function, has the directions round up to the next integer no matter what the decimal is. So some good examples. If we had the greatest integer of 4.8, round that up to the next whole integer that's bigger than 4.8. That's 5. And if we were to take the greatest integer of, say, 3.1, what's the next integer that's bigger than 3.1? That's a 4. It doesn't matter that it's a 0.1. Yes, back in elementary school, you did all these pieces with rounding that says, oh, which is it closer to? 3.1 is closer to 3, so I'm going to round down to 3. We don't care about which is it closer to. We don't care about the elementary school piece of rounding. We are saying, no matter what, round up. Even if we have negatives, if we were doing something like the greatest integer of negative 2.15, what is the next integer that's bigger than that? The next integer that's to the right of negative 2. Well, to the right of negative 2.15, you have negative 2. And if we had the greatest integer of negative 8.9, what is the next integer to the right of negative 8.9? It would round up to negative 8. That is the greatest integer function. This is the most common notation for it. Our textbook does not use it, but once in a while you will encounter a piece that says, this is the notation for it. I bring this observation out in case you choose to search the internet for some other pieces and some website is using this notation for it. This notation is also sometimes used for the greatest integer function. And they choose to use that one because there is also another function called the least integer function, which is sometimes called the floor function, and they use this notation for the floor function. That tells you instead of round up, round down. We will not be working with the floor function though. And since we are not working with the floor function in red, we don't need to have the two different notations to help us out with the little sidebar at the ceiling or the little sidebar at the floor telling us round up, round down. We're going to stick to this notation on the left-hand side with the double bar square brackets. Now that we have an understanding of what the greatest integer function is, show that the limit as x approaches 2 of the greatest integer function does not exist. Okay, so once again we could say left-hand limit, does it actually equal the right-hand limit? Well, we're actually told show that it does not exist, so we're told this is not going to be true. Well, let's think about why. As we're approaching 2 from the left, we're looking at x values that are we're looking at x values that are like 1.9, 1.99, 1.999, dot, 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 keep going. Round to the next biggest integer. That's a 2. 1.99 rounds up to a 2. 999 rounds up to a 2. And no matter how many 9s we start throwing on this piece, coming from the left, the greatest integer function is always going to approach a 2. But if we build a greatest integer table coming from the right-hand side, that's looking at pieces like 2.1, 2.01, 2.001, and so forth. We still have to go up to the next biggest integer. 2.1 is required to round up to a 3. 2.01, still bigger than 2, it rounds up. 0.001, although barely beyond 2, is still there, beyond 2, so it rounds up to 3. And it doesn't matter how many zeros we start attaching to it, it's always going to be something that's a tiny, tiny, tiny bit bigger than 2. So they're always going to round up to 3, and this is why the limit does not exist. The left and right hand limits don't match up. In terms of the graph for this piece, it's actually a type of step function where we would have from 0 to -1, -1 to -2, -2 over to -3, and it's going to wind up looking like a step function. And I can't really draw my open circled versus closed circle. They're a bit confusing there, but there we go. Last two pieces. Here are two theorems. If f of x is less than or equal to g of x when x is near a, except possibly at the actual function value, and the limits both exist, then the limit of f of x has to be less than or equal to the limit of g of x. That's a piece that a lot of times students don't really understand until we start putting some pictures to it. So let's say we have this graph of here is f of x. And then here is the graph of g of x. Okay? If we are looking at the limit as x approaches 1, what is happening to it? Well, if we look at this area very, very close to the left and to the right, do you notice how the graph of g is above the graph of f of x everywhere on the inside of this piece? We don't care about what's going on far away from our x value. But just inside the lines for this little area, the height of g is always above the height of f. Well, if blue is above black everywhere that we can see, doesn't it make sense that this limit here has to be higher than the limit, put that in the wrong spot, than that limit there? That's what this first piece is telling us. If we have a function that's up higher than another one, the limit is going to be greater. That's all. Draw another picture to help perhaps visualize it better. If we have this graph, and we have another graph, this is going to split the piece up into two sections. The left-hand side, green, is always above blue. Because green is above blue everywhere, if we were to take the limit of green and the limit of blue, green will have to be bigger than blue. That's just saying if we start limiting in here and limiting in, the height of green is above the height of blue. That's all it's saying. This is going to be the basis behind an incredibly important theorem, an incredibly important strategy. The squeeze theorem. Sometimes the squeeze theorem will be called the sandwich theorem or the pinching theorem. Regardless of the name of it, it has this idea that if you have a function that is in between two other functions, and the two functions are limiting in on the other pieces, let me draw the graph, it'll be easier to see. Let's say I have an upper function, and I have a lower function. In this one, green is above blue everywhere. This would be like saying here is our f of x, here is our h of x. Suppose we have a third function that's in between them. This is our g of x. If we wanted to take a limit, we know from the previous one that the limit of g of x is going to be less than, I'm writing that wrong, the limit as x approaches 0 of g of x has to be less than the limit as x approaches the same value of 0 of h of x, because h is higher than yellow. But at the same time, we also know that the limit as x approaches 0 of f of x, that's still got to be less than the limit of g, because yellow is still higher than blue. The idea behind the squeeze theorem is to say, suppose that this blue one, that this blue one actually didn't stop down here, because right now we can see in between the blue and the green, there's this big gap. What if it wasn't a big gap? What if it actually came and connected like this? What if we actually had the limit of f of x as x is approaching 0 equal this other limit of something that's higher than it, of h of x. In this instance, the way I've drawn it, they both have the limit of 0. But we further know that everywhere the graph of yellow is in between them. Noting over on the left, yellow is in between the green and the blue. On the right, Yellow is in between the green and the blue. And as we get closer and closer and closer to our window, we're noting that in this tiny little area here, in this tiny little window, this tiny little neighborhood, it still holds out. Green is above yellow, is above blue. But because green and yellow are squeezing together and actually getting to the same point, yellow has to be in between them, so it's got to be the same piece. It's just saying green, blue, yellow. If we squeeze the green and the blue together, yellow's going to get squeezed in with them, and so all three of them are going to be at the same point. That's what the squeeze theorem tells us. If you have a function that's in between two others, but the other two squeeze together to have the same limit at a particular point, like x equals 0, if this happens, then we know the third limit that's in between them, our g of x, it also has to be the same thing of 0. Where this gets to be particularly helpful are problems like this. Show that the limit of x squared times sine of 1 over x equals 0. Students may remember that when we were going over the sine of 1 over x in class, we had a piece where we used the tables to say, well, where is it going? And we had a graph that kind of looked like something like that. Well, actually, it was it had something that was kind of messed up like this. Okay? And we discussed before that if we just look at certain x values, it looked like it was going to go to a 0. It looked. But when we did further investigation based on some of our homework that we were doing in class, we actually saw that if you start zooming in on this little box, this bouncing back and forth pattern keeps going. And if you zoom in even more, the bouncing back and forth pattern keeps going. The limit as x approaches 0 of sine of 1 over x actually does not exist because it never starts closing in, it never stops bouncing back and forth. But where this piece gets helpful for us is that this is not just sine of 1 over x. It's also x squared times. What this winds up doing for us is, as you start getting really far away, sine of 1 over x, because sine of everything, sine of anything is bounded between -1 and +1. So when we are looking at the sine of x squared, we actually have a piece where it's getting like really huge, and then as it gets closer, it kind of tumbles down on this, and then it starts getting really huge again, bigger and bigger and bigger, farther and farther down forever. But what we are most concerned with is this tiny little area. Please note, this is a piece that we could say, if we took, I'm trying to think of a good way of phrasing this. If we had the limit as x approaches 0 of just negative x squared, it's going to look like this. Or rather, if we take f of x to equal negative x squared. If we take h of x to equal positive x squared, we'd wind up with a graph that looks like this. But the graph in the middle, x squared times sine of 1 over x, because we're taking an x squared and multiplying it by some number for the sign, but that some number is always between positive and negative 1, that actually causes the graph to have this crazy bouncing behavior back and forth where it gets smaller and smaller and smaller. And it looks like this. Do you notice how in this particular problem we can see blue is always above yellow, yellow is always above purple? If we have these equations then, our limit of f of x, which was the function that we decided as negative x squared, that closes in on a 0. And if we take the limit as x approaches the 0 from h of x, the top function, that was x squared, it also goes down to a 0. Well, if purple is coming up from the bottom to get to 0, blue is coming down from the top to get to 0, but we also know that yellow is always in between purple and blue. Well, then we're going to have our limit as x approaches 0 of x squared times sine 1 over x. It's got to be some number that's in between 0 and 0. There is no number in between 0 and 0. So if it's got to be between 0 and 0, the only thing that it could possibly be is also 0. That's what the squeeze theorem does for us. Although we don't know what this function is going to, although we don't have a way that we could do a direct substitution, because if you tried plugging in x equals 0, you'd have sine of 1 over 0. You can't take over 0, so direct substitution does not work. And because it's a trigonometric function, none of our other properties worked for that either. Because sine of 1 over 0 doesn't, we didn't have anything that would work, but this piece will. We can sandwich the yellow in between the blue and the purple, and then when we squeeze the sandwich together, they all get crushed down to the same point. That's what the squeeze theorem notes for us. There was a lot to go over today. We had these theorems that discuss the height of limits, specifically the squeeze theorem. We had the greatest integer function. We discussed left and right hand limits to show that limits don't exist. We did a lot of pieces with conjugating, with indeterminate forms having 0 over 0 where we needed to use some algebra. But all of these pieces were designed so that we could start looking at the limit properties like direct substitution, like, excuse me, like having square roots, like having powers, like having constants, like. We had the 11 limit laws to look at, 2 limit properties, and 3 limit theorems. The goals behind what we had today were to know what the laws are, but most importantly, be able to look at a problem and recognize when a particular law, property, theorem will actually be beneficial. If you can recognize them, then you can use them, you can apply them. Know, recognize, and apply the 11 limit laws, 2 limit properties, 3 limit theorems. Take those 15 things and actually use them to calculate limits. That was the goal behind our work today.